Let's take you back to linear momentum. Remember linear momentum? We use the letter what? P. We say it's what? Mass times the velocity. When an object is moving, it has a moving power. And that moving power is equal to mass times velocity. So when they hit you from behind, when you stop at the light and they hit you, you feel that bump there because that car has a good mass with some decent speed and they're moving at you, you'll feel it. Or when somebody tackles you, if you're playing football, they grab you and wrestle you and tackle you to the ground. They have a mass of 75, 80 kilogram running at 10 miles per hour. They're going to hit you and grab you. So that's their moving power. Now if you go in the opposite direction with the same speed and the same mass, you get even twice the pain because you're going to hit them, they're going to hit you. You know, so it's like having one object twice the mass with double the speed. So what about something spinning? Does it have moving power? You want to feel that, you take a blade that's spinning like, we're not going to cut your fingers, but a ceiling fan, and it's spinning, and you stick your hand there. Does it hurt? Better hurt. Why? Because that's moving power, spinning. So what is that called? The angular momentum, spinning. So it has some moving power because it spins there. So what is the equation for angular momentum? Well, for angular momentum, and we use the letter, notice for linear momentum we use the letter what? P. Guess for angular momentum what letter we're going to use? L. I know you're thinking, why not use L for linear momentum and use P for that one? Well, we're a little bit backward. So we use L for angular momentum. And the angular momentum is equal to, notice it's mass times velocity. When things are spinning, we don't use the mass, we use inertia. Instead of velocity, we use what? W. It's the mass times the velocity, it's the inertia times W, the average speed, angular speed. Now, let's see if I can open it more. So inertia is I times W. And inertia is really, unless you have a specific shape, the inertia is the summation of m times r squared. That's what the inertia. So if I replace the inertia with that, and take actually this one, replace it with V over R. That's what, remember, V equals W times R, which means W equals V over R. It's going to be mass times R squared times V over R, which ends up being mR times V. MRV. What is linear momentum? Isn't that m times v? So if you take the m and the v, because you can rewrite that what? R times m times v. What's m times v? That's linear momentum. So R times P. So there is a relationship between angular momentum and linear momentum. Angular momentum is equal to R times the linear momentum. And that's the derivation behind it. Angular momentum is also I times W. And again, you want to picture what that is. If you have a merry-go-round, or what is that game at the park you go and you spin it, has a little, not the merry-go-round, but in the park you see people standing there, spin, And sometimes you try to spin it faster, people go flying off it. I forgot what it's called. I used to put my nephews and nieces, keep spinning them as fast as I can until they go flying, because then the friction force is no longer large enough to hold them there. But if they're sitting at the edge here, and this is R, and I'm spinning them with a high rate of speed, W, if they go flying from here, they're going to travel in that direction. That's where linear velocity is going to be. Tangential. In that direction. Tangential, actually. Tangent. The other one doesn't look like a tangent, like a 90-degree angle. That's where the velocity will go. They'll go shooting in that direction. We're saying that if they go flying in that direction, the person goes flying in that direction, they have a linear momentum, which is mass times velocity. So if they go flying and they hit you or hit a little kid, the other kid's going to cry because their mass times their speed. That's how much moving power they have. While they're spinning too, they have what we call angular momentum, linear momentum. If you dangle a kid over them as they spin around, you hold them like this and they hit their feet, they'll feel that power too. And that's where the angular momentum is. The angular momentum is the inertia times W. Well, what is the inertia for a shape like this? Well, they're sitting on a disk, right? So the inertia is the inertia of the disk, which is 1/2 mr squared, plus the person who's sitting there. And the inertia of that person is the mass of the person times r squared, the distance. So the sum of the two, that's the inertia for the whole system. Times how fast they're spinning. And again, you can tie the two things together. You can find L if you know P. You can find P if you know L using that equation. Notice I drew this on a 90-degree angle. What about if the thing is not really 90-degree angle? Sometimes you're pulling on this like on a different angle. So let's see what will happen to that angular momentum. I'm horrible with drawing things. So, but let's say we have someone's going a circle there. And this distance from here to there we call it R. But now, instead of pulling like we had the weight, remember the previous example, we had the weight straight down? What happens if we didn't have that force straight down? We had it on an angle, pulling up or down. Let's say it was pulling in that direction on an angle. That's the force. We'll call it P, pull. And that's the angle theta. Maybe that's a clothesline or a belt going around this one. Something is attached to it in that direction. So it's going, you're pulling in that direction, try to loosen this one. What we need to do first is find what portion of that pulling force is the tangential one. It's in this direction. And notice that's the y value. This is the x here, and this is the y. I'm looking for that value right there. So that value will have to be what? P sine of theta. This value is P cosine theta. I don't care about this value here. This has no torque because the pivot point is right there. It goes through that pivot point. Notice it goes through the center of that circle there. So this has no torque. So what is my linear momentum here? Becomes? Oh, angular momentum, what's my angular momentum? We'd said the angular momentum will be R times P before, right? Not in this case, because this angle has to be P times sine of theta, because you are an angle there. And we can derive that equation. Now again, you got to be careful. If we give you the angle, the same problem, because I want you to think, oh, it was sine. if the angle we given you, instead of giving you the angle with respect to the x-axis, we gave you this angle. You know what? We said this angle was theta here. So this value becomes what? P cosine theta. Why the cosine? Because this is the adjacent. Before that was the opposite. So in this case, this will be L equals R times P times cosine theta. So be careful. Is theta with respect to x? If it is, it's always the sine. If it's with respect to y, it's always the cosine, because the adjacent is the cosine over the hypotenuse. Here, the side that you're looking for is the opposite to this angle, and that's the sine. But our book always gives you the value theta with respect to that. So you can write that, in this case, this is mass times velocity, R times M times V times sine theta. Linear momentum is mass times velocity. Here, this will be R times mass times velocity times cosine theta for this example. I'll take an example in a minute and go through it. Okay. Let's take an example. We have a merry-go-round. Here's my round merry-go-round. I'll give you the mass and dimension of it. The radius of the merry-go-round here is 2 meters. That's the radius. Now this kid decides he's going to jump on the merry-go-round. But he came in from this direction. He was running, so this kid, instead of straight at 90-degree angle, came in on I should have made the picture nicer. Wait. Here's the merry-go-round. There's the radius. You get to see the angle better here, 2 meters. This kid decides to come and jump on it, but it came in from this direction. So this kid came running, has a mass of, let's see, 21 kilogram. It has a speed or velocity equals 4.1 meters per second, and decide to jump on the merry-go-round. Now let me give you the angle that we have. So his path there, if you continue, that's the direction of his path, in that direction. R is in this direction. So this angle here is 128 degrees. That's obviously with respect to x. And the question for this, can you tell me what the angular linear momentum is? I mean the angular momentum, not linear. What is the angular momentum is? Not linear. L always gets me linear. Since the angle with respect to the x-axis, we say it's what? R times P times the sine, not the cosine, times the sine of theta. And P is what? Mass times velocity. Do we have these pieces? Do we know what R is? 2. The mass is the mass of the person, because we're talking about his linear momentum. The mass of the person, which is what? 21. The velocity of the person, he's the one creating that angular momentum. The thing wasn't spinning. He jumps on it, and it's going to start to spin. So his actual reaction is going to make it spin. That's why we're using his mass, his velocity, times the sine of 128 degrees. $145.6. Kilogram meter squared per second. Remember, this is meter per second times meter, that's meter squared per second, and the mass in kilogram, and the sign has no units. Again, in case you missed it, here's the units. Why I wrote these units? Look at the equation. What are the units for R? Meter. What are the units for the mass? Kilogram. What is the unit for velocity? Meter per second. And the sine has no units. Unitless. Sine, cosine have no units. It's a side divided by a side. No units for that. So it's kilogram m squared over s. Remember the inertia in linear? Inertia? We said what? I'm done with this example. I'll leave it. I'm going to finish the last piece here and send you home. You're getting quiet now. I can tell you're getting tired. We said F times the time equals what? The change in linear momentum. F times T or delta T, whatever you want to use, equals mass times V final minus mass times V initial. Remember that one? I can look for it. And that was impulse. Where is that? What chapter? Where was that? Come on. I'm sure it's under momentum once I find the chapter. Linear momentum, where are you? Come on. Linear momentum, chapter 9. So you guys from night class probably missed it. Here we go. Impulse equals F average times delta T equals delta P, and P is mass times final velocity. I'm sure that equation is written somewhere here, times mass times initial velocity. We have it written somewhere. Where'd you go? Where did you go? Was it on the bottom? That's just an example for, yeah, mass, final momentum minus the initial. In this case, the initial was 0 because the velocity was 0, but mv final minus mv initial. But I thought I saw it somewhere written there. I mean, this is the one, and change of linear momentum is mass times v final minus mass times v initial. That might be written actually somewhere. Where is change of linear momentum? When I'm looking for equation quickly, I know where, at the back of the book. I'll have it in the back, in the summary. Come on. Come on. Oh, they just left it like this. Just left it like this. I thought I just seen it MV final minus MV initial. No, they just left it as change, which is MV final minus MV initial. That's what the change in linear momentum. The average force times delta T. Well, here, when things are spinning, we have one similar to that. Instead of force times delta T, we're going to use torque here. We said Newton's second law says the net torque equals inertia times alpha. And torque is change in linear momentum, angular momentum, over change in time. So if you cross multiply, you go inertia times alpha times the change in t equals change in angular momentum. The letter L is driving me nuts. And delta L means what? L final minus L initial. And what did we call I times alpha? Isn't that torque? Isn't I times alpha is torque? So torque times delta T equals the change in angular momentum. Just like this for linear, this is for angular. This is the equation for linear again. Torque times delta T equals the final angular momentum minus the initial angular momentum. The final minus the initial. L final minus L initial. And we can calculate L final, depends if you have an angle, no angle, RMV sine theta. V final minus RMV initial sine of theta if you're on an angle there. If there's no angle, you're good there. And that's the equation. Actually, I'm trying to get one similar to what we did in chapter 9, and that's this one. And this one actually is this one. No new news. I'll do an example on that and we're done for the day. Just want to derive that equation. Let's see. What do we have? We have a windmill. There we go. And if you've ever seen the windmills, you've probably seen them on the roof of the house. They'll be sitting like this, and they have like color things, and they spin, constantly spinning if there's wind there. So this one has a torque, average torque on them of 255 Newton meter. It's making it spin all the time. It's a nice breezy day, and that torque is 255 Newton meter. Assume the windmill initially at rest. Initially at rest. The question is, what is the angular momentum, L? After, I don't know, 2 seconds? So this is what I know. There's something torque and spinning and time and angular momentum. That's what I'm hearing from this problem. I know there's one question that puts all these together, and that's torque times delta t equals the change in the angular momentum. My torque here is what? 255. My delta t, which is what? 2 seconds, equals L final minus L initial. Well, L is what? We said I times W. The first thing we said today, angular momentum is I times W. Well, if the first one initially at rest, what was W? 0. So initial one was I, whatever the inertia, I don't care about the inertia, times 0, which is what? 0. And then they're asking me what is the final speed. This is what is the final angular momentum. They're looking for L final. So 255 times 2, which is what? 510 equals LF, which is the final momentum, minus the initial, which is a 0. I just did that here. So what is my final momentum? 510. Now if you tell me what is the shape of that windmill, or how fast it's spinning, if you tell me the shape of it, maybe if it's a round one, I can calculate what the inertia is and tell you how fast it's spinning. Or if you tell me how fast is it spinning there, I can tell you what the inertia for that. Because this one equals to I times W final. So I need to know one of these to get the other one. You tell me the shape of it, I'll tell you what the inertia is. You tell me how fast spinning, I'll tell you the inertia. You tell me the inertia, I can tell you how fast it spins. And that's the end of the windmill. We still have 2 more sections, and they are decent sized sections, so I think I tortured you enough today. Hoping to hear something about